Now that we have a good grasp of what GNBAs are and how they operate, let's see how we can build from any LTL formula psi a GNBA auth psi that captures psi's behavior, in that it accepts precisely the atom set traces of infinite sequences that satisfy psi. Like any GNBA, auth psi is a 5-tuple having an alphabet sigma, a set of states q, a set of initial states I, a transition relation arrow, and a set of accepting sets calligraphic f. The alphabet sigma will be taken to be the power set of atoms, which means that words over this alphabet are essentially atom set traces. We still need to define the other components of auth psi. But first, let's spend some time building intuition on this automaton's construction. The main idea is the following. We ask ourselves, under which scenarios can we have the formula psi be true or false on some infinite sequence starting on some state? For this, we look at what happens within its subformulas. So what we'll do is, for all subformulas of psi, consider all the scenarios of them being true or false in a manner that is consistent, in the sense that it is not self-contradictory. I'll illustrate this idea next with some examples. But first, some notation. We'll often write bar on top of a formula instead of the negation symbol followed by the formula. So for any formula phi, bar phi will be the same thing as not phi. It's just a notation for not phi. And importantly, we will identify a doubly negated formula, not phi with phi. So not phi will be the same thing as phi. And this is okay because of the double negation property. Also, to be sure, this is what I mean by subformulas of a formula. I mean all the formulas that appear as part of psi. For example, an atom A has only one subformula, A itself. Always A has two subformulas, A and always A. Always eventually A has three subformulas, A, eventually A, and always eventually A. Always, not always A or B, has six subformulas shown here. Okay, A is one subformula, B is another formula, a subformula, always A is another subformula, and so on. As an exercise, please define this concept rigorously. What type of definition is needed here? Now some examples of this scenario idea. Let's take the formula psi to be always A for an atom A. And let's see what it takes for always A to be true. That is, what are the scenarios under which always A is true on some infinite sequence that starts in some state? Well, to have always A true, we certainly have to demand that A is true right now, in the current state. And we'll also demand that always A is true in the next state. Of course, when we move to the next state, meaning the next state will become the current state, we'll demand that A is true there as well, and so on. But right now, from the perspective of our current state, all we can ask are these two things, that A is true right now, and always A will continue to be true in the next state. Now, let's see what it takes for always A to be false. we have two possibilities. We either demand A to be false right now, which immediately makes always A false, or allow A to be true and leave the goal of falsifying always A to the next state of the sequence. So our analysis has shown three possible scenarios that make sense, in that they are consistent in the current state. Either always A and A are true, or always A is false and A is true, or finally, both A and always A are false. These scenarios only refer to the current state. There will also be some requirements on moving forward to the next state, which will include the demands shown above in red, this bit and this bit. Note that, for example, the combination of not A and always A, meaning that we want A to be false and always A to be true, is not a consistent possibility. It cannot be the case that always A is true, but A is false. For another example, let's take psi to be eventually A, and let's see what it takes for it to be true. To achieve the truth of eventually A, we either demand A to be true, and we are done, because eventually is implied by now, or alternatively, we allow A to be false right now and postpone to the next state the goal of making eventually A true. On the other hand, if we want eventually A to be false, we must demand that A is false, and then also that eventually A stays false in the next state. This analysis yields the following three possible scenarios for the current state: A and eventually A, not A and eventually A, and not A and not eventually A. And again, each of these scenarios comes with its own set of requirements that need to happen next. Again, the red part of the analysis shown on the slides. So we can distinguish between what we put in the actual scenarios, which is about the now, and some requirements about what we need to happen next. And as before, we can identify an impossible scenario, namely this one, A and not eventually A. These cannot coexist, these two situations, since A being true makes eventually A be true. So this combination would be inconsistent. By the way, you probably noticed some similarity between the analysis we made for eventually A and that for always A from the previous example. As homework, please think about how these two are similar. Okay, you probably start to see the pattern of what we are doing here. We compute all possible scenarios for the current state and also note some things to be postponed to the next state, things that we can call unfinished business. For example, in the scenario where we want eventually A to be true and also A to be false, the unfinished business is that eventually A must be true at some point. So we postpone it to the next state, since we have not achieved it in the current state. For how long can we postpone it? Well, certainly not indefinitely, since A must eventually become true. But this is another question about the global behavior. For now, we only looked at the local aspect. What are the possibilities in the current state and what can be postponed? Let us look at another example. Taking the formula psi to be always eventually A. For this to be true, we must demand eventually A to be true, right? because always eventually A also means right now eventually A. So this is a must. If we want always eventually A to be true, then eventually A must be true as well. In turn, for eventually A to be true, we either demand that A is true, or allow A to be false and postpone eventually A to next, as discussed in the previous example. Going back to always eventually A, we must also demand that it stays true in the next state, because this is the nature of always. On the other hand, for always eventually A to be false, we either have eventually A be false, meaning that A will also be false in this scenario, or we go for the alternative scenario, allowing eventually A to be true and leaving the goal of falsifying always eventually A to the next state. And further looking into what it means for eventually A to be true, we have the possibility of making A true right now, or allowing A to be false, and postponing the goal of making eventually A true to the next state. So we have gathered the following possible scenarios for right now. A eventually A, always eventually A, not A eventually A, always eventually A, and so on. So these 5 scenarios have been produced by our analysis. And we also have some unfinished business shown in red. Know that when investigating the scenarios, we look at what can happen to all subformulas. In this case, always eventually A has 3 subformulas: itself, eventually A, and A. When analyzing possibilities, we consider both these subformulas and their negations. The above combinations are possible scenarios. Other combinations are not. For example, the combination not A, not eventually A, and always eventually A is not consistent. As an exercise, please think of why this is the case. Also, can you indicate other inconsistent combinations? Let's consider a final example, taking the formula psi to be always, not always A or B. We're doing the same kind of analysis, chasing through all consistent possibilities down to what happens to any subformula of this formula. So for our formula to be true, for our big formula to be true, one scenario is to have its immediate subformula, this one, be true, which itself has 2 subcases because it is an OR. The right side, not always A, can be true, which means that always A will be false, which happens if either A is false or if A is true plus some unfinished business postponed to the next state, namely that not always A will be true in the next state. Or we could allow not always A to be false and demand that B is true. Back to the top case split in our scenario, instead of demanding that this immediate subformula be true, we could alternatively postpone making our big subformulas. This one, we can postpone the goal of making that one be true, or we can postpone it to the next state. This is only half of the analysis, since we have not analyzed the scenarios that make our big formula false, which I will not show here. So here are our possible scenarios collected here that make our big formula true. Again, not showing those that make the formula false. There are 5 of them, and I've shown them here with numeric labels that suggest which part of the above case analysis they correspond to. In all cases, not only the big formula must be true, but also its immediate subformula, this one, must be true as well. This is by the nature of always, since our big formula has an always at the top. Now, this scenario corresponds to case 2 in our analysis, where we are in the case where B is true, not always A is false, which makes always A true, and then A true. So we just collected all the consequences of that case as part of this scenario. On the other hand, in case 1, in our analysis, we must have not always A true and A false, which means A true. Which means not A true. But there is no requirement for B. So in this case was independent of whether B is true or false. So we go either way in our scenario. In one variant, we take B to be true, and in the other variant, we take B to be false. And similarly, for case 1, 2. Note that the scenarios that we consider are complete in the sense that they decide the truth or falsity of all subformulas of psi. This is why, for example, cases 1, 1 and 1, 2 in our analysis have branched into 2 scenarios, depending on the truth or falsity of B. So these 2 scenarios correspond to case 1, 1 in our analysis, for example. So no subformula is ignored. And again, these scenarios must also be not only complete, as I just said, but also consistent, meaning that they do not contain contradictions. For example, they are not allowed to contain both phi and not phi for some subformula phi. And they are not allowed to contain, for example, always phi, and at the same time not contain phi. Okay. I hope you have an intuitive grasp of the kind of scenarios we need to consider for the truth of the subformulas that appear in a formula psi. You will not need to perform this tedious case analysis that led to these scenarios in our examples. I've only shown this to give you some intuition. Next, when we define our automaton, aut psi, we will use these ideas to give a more direct definition.